Breakthrough, Understanding the Quantum Rainbow. I'm Steve Blair, welcome to Breakthroughs. Researchers investigate light-emitting defects in materials that could be used for quantum computers and quantum networks. Future quantum devices will need reliable, controllable systems that can store and convert quantum information, ideally at room temperature. One of the most promising systems is hexagonal boron nitride, which has defects capable of emitting single photons, or a single quanta of light, at a time at room temperature. Unfortunately, defects in hexagonal boron nitrate have a problem. They emit light in a rainbow of different hues, and researchers haven't been able to figure out how to predict or control which color they emit. Now researchers at Harvard J.A. Paulson School of Engineering and Applied Sciences, SEAS, and Stanford University have developed a method to find the defects in a nanometer scale precision and qualify and predict their color spectrum. Wow. This research was published in Nature Materials. Previous research suggested that hexagonal boron nitride's rainbow emissions could have something to do with local distortions and strain near the quantum defect, which can drastically change the behavior of the emitter. The problem is identifying the defects that give rise to quantum emissions is like searching for a friend in a city without a cell phone. You know they're there, but you have to scour the entire city to find their precise location. The researchers used theoretical and experimental techniques to understand the properties of these emitters. By combining calculations with advanced microscopic methods to visualize the material at different length scales and under different conditions, the researchers were able to trace the colorful emissions to specific atomic defects and investigate their properties. We needed to know how these defects coupled into the environment and if they could be used as a fingerprint to identify and control them, said Christopher Cicerno. Using a modified electron microscope developed by Dion at Stanford, the scientists were able to correlate the local atomic scale structure of hexagonal boron nitrate with its emission spectrum. Through hundreds of experiments, they bombarded the material with electrons and visible light and recorded the luminescence. They also used diffraction experiments to study how the periodic arrangement of atoms in hexagonal boron nitrate influenced the emission color. The challenge was to tease out the results from what can seem to be a very messy quantum system. Just one measurement doesn't tell the whole picture, but taken together and combined with theory from Nagarim's team, the data is very rich and provides a clear classification of quantum defects in this material. This process to predict and classify these quantum spectra could be transformative for a wide range of quantum materials, said Naring. It's an exciting time to be a theorist. New microscopies that measure structure property relations at a scale in single atoms are a great testbed for our predictions and drive our knowledge of optically excited quantum materials forward. The research lights the way towards atom-by-atom design of quantum materials. Oh man. Wow. I'll leave a link to the full article in the description, and as usual, please like, share, subscribe, and take care.